Okay, ladies and gentlemen, Jack Tuszynski is going to take us through 100 years from quantum physics to quantum biology, how long to quantum medicine. Take it away, Jack.
Thank you, Kim. It's a great pleasure to be back here in your fantastic course. And the answer to quantum medicine actually is 3 months, I think.
Yeah, when the book comes out.
Yes, exactly.
That's right.
Exactly. And we have these books that I co-authored in the past, and they talk about different aspects of quantum biology, from nano-neuroscience to topics in consciousness, biophysics of consciousness, and I hope we will have time in this lecture series to touch more about consciousness than in the past.
Mm-hmm.
I was a bit gun-shy, now I'm less so,
good.
and that's the reason, because Quantum Body, the book that I co-authored with Deepak Chopra and my good friend Brian Fertig, who is also a medical doctor, as Deepak is,
Mm-hmm.
endocrinologist, both of them.
Right.
We wrote this book that is coming out December 5th in North America. You can buy it, pre-order it on
Right,
Amazon.
I've already pre-ordered.
I'm not trying to have a sales pitch. It's just something quite different, as hopefully you will appreciate. It's a fusion of ideas from physics, medicine, and Eastern philosophy. So I contributed to physics, as you can imagine. Not so much medicine or philosophy. So anyway, everything quantum these days, finally, after a century or so, is becoming fashionable, even sexy, I would say. Mm-hmm. And today and in the next 3 lectures, I'll be talking about quantum biology. But before I can actually jump into the topic, I will say quite a bit about the foundations, because we need to know where it all originated and why. There is a reason, historical and scientific. So within the last 120 years, I mean, physics, and without bragging, it's my field has been probably the most sophisticated and advanced field of science, and it has the longest history, starting with natural philosophy and as physics as such, maybe 350 years dating back to Galileo and Newton. And that's what we call classical physics. Classical physics spanned the first quarter millennium, 250 years or so, and quantum physics jumped on the scene with the beginning of 20th century. So 1900 precisely is the year that quantum mechanics, quantum physics was born. It underwent changes of the name. Initially was called wave mechanics, actually, not quantum. Later on, quantum mechanics. Now, quantum physics. Mechanics is associated typically with things like car repair and so on, but has nothing to do with this. Mm-hmm. And the most advanced reincarnation of quantum physics is called quantum field theory. And then there's an ongoing effort to achieve something called the theory of everything. And because we still are not there yet, there is no fusion between quantum physics and gravity. Gravitational concepts are still not incorporated. But as you can see from the list, quantum physics jumped to chemistry and sort of colonized chemistry. All of chemistry is quantum. There's no chemical bonds without quantum interactions, without electron sharing, etc., which I will touch on briefly. And then more recently, people noticed that quantum effects play a role in physiology and how our senses work. Individual quanta of light are perceived by the eyes. Individual quanta of molecular vibrations are perceived by the sense of olfaction, the smell, etc. So physiology, of course, you might say these are peripheral things, but not really, because we perceive the world through our senses, and our senses are so finely tuned to the stimuli coming from the external environment that individual quanta or several quanta can be detected. And to me, as I'll try to convey later on, it's not a mystery, although some people think it is, most people probably. The mystery to me is the amplification of these tiny, tiny signals. I'll give you a sense of dimensions later on. Today, I think I'll just try to give you a historical perspective, a little bit of forward-looking statements and general overview of the subject, and later on we'll talk about more technical aspects once we understand that. And from physiology, of course, you go into biology, because physiology of the human body is really based on the cell biology and fields related to it, immunology, etc. But biology, so chemistry transitioned into fully blown quantum paradigm around after the Second World War in the 1950s. Biology became acquainted with quantum physics about 15, 16 years ago or so, maybe not 20, about 15, 16. And it's still undergoing some birth pains. I wouldn't say it's a fully fledged field of science. It's a nebulous field which is not very well defined, and we'll talk about the definitions of quantum biology. It means different things to different people. I'll tell you what it means to me later on. And then, of course, in the public parlance, we're familiar with quantum computing more and more, as well as cryptography, quantum cryptography, the promise of unbreakable codes performed by quantum cryptography devices. And then, starting with these books like The Emperor's New Mind, and later on research articles by Sir Roger Penrose, Nobel Prize in Physics of 2020. I cannot resist to mention that I published a paper with Roger Penrose last year, which is, wow, I would say, one of the highlights of my career. Yeah. So he actually pushed forward a lot of ideas about consciousness from a very rigorous scientific point of view, arguing that consciousness cannot be understood within the classical paradigm. Classical neuroscience, classical physics, and neurophysiology is lacking something. These books did not reveal specifically a mechanism that would explain consciousness. We still don't know, but they paved the way toward it. And arguments are made very forcefully about the inclusion of quantum effects. And specifically, he mentions non-computable processes in the brain. The human brain, as probably all of us intuitively perceive, is not a computer, is not a device, it's not a machine, it's not deterministic, it's not programmable. We make mistakes, like it or not. We have feelings, we have experienced the world subjectively. So that all of these things are very eloquently articulated by Penrose's books and papers, and that led to the speculations, largely I would say resisted by the neuroscience community, about what I would call the quantum brain, or quantum aspects of consciousness, neuroscience. Neuroscientists typically shy away from using the word consciousness. Cognition or information processing, things like that, right? But not consciousness. Consciousness is a domain of philosophers, spiritual people, typically religious arguments are made. I'm not going to talk about this. This is not who I am or what I talk here in this lecture series. I'm a scientist, I'm a nuts and bolts physicist. I want to understand how the brain works, including how it processes information and how it makes often subjective decisions. So we'll get into the nitty-gritty a little bit later on. Why is there quantum anesthesiology listed in that slide? Because it's very, very close to consciousness. As probably all of you know, anesthesia is one controllable way of switching consciousness off and on. Not only in humans, by the way, the same anesthetics and roughly the same concentrations work on pretty much all animals. And you might be surprised, also plants. They also turn off perception of and reaction to the environment by plants. I didn't know it, but my good friend Bruce McIver from Stanford, he's a neurophysiologist, wrote papers about this and studied it. So consciousness, elusive, but very important, and we know how to control it. In fact, we control it with incredible precision. Anesthesia is a branch of medical science, which is probably one of the most accurate branches of medical science. Correct me if I'm wrong, but without anesthesia, there would be no modern medicine.
Yep.
So, still unexplained largely. We know more or less, but people argue, and again, I will say a few things about what is and isn't considered a mechanism of anesthesia, or a mechanism. Again, Bruce McIver studied this field very extensively, and he uses the phrase sufficient but not necessary. In other words, there are many ways of inducing anesthesia, including hitting your head with a hammer. So there is sufficient ways of inducing anesthesia, loss of consciousness, let's say, right? But not necessarily all or any of them may always play a role. Sometimes yes, sometimes not. Membrane receptors, membrane stiffness changes, slowing down of action potential arrivals, etc. All of this has been discussed. And at the end of this list of topics, you have quantum psychology and psychiatry. I think these are the fields that would, in my opinion, benefit greatly, maybe not necessarily from verbatim introduction of quantum physics concepts such as, Schrödinger's equations or Heisenberg uncertainty, but they do, in my opinion, stand to benefit from many ideas, which are not deterministic, not classical physics, but quantum physics. And I'll try to elaborate on this later on. So let's start with in the beginning. Let's begin with the beginning. So what was physics like before quantum mechanics? Some of the names and some of the fields are probably familiar to you to some extent, maybe not all, but it's all started with classical mechanics. Things that I think most first-year students consider very boring. When you take physics 101 or whatever number is used in this particular institution of higher learning, it will start with mechanics, with things like forces, energies, momentum, velocities, etc. The credit has to go to, in my opinion, the greatest mind that ever inhabited this planet, Sir Isaac Newton, because he single-handedly created this field, which today has applications, even today, in things like engineering, construction. We have to obey Newton's 3 laws of mechanics, but also created the tools to analyze physical systems, namely calculus, mathematics, and created optics. So several fields, nobody has achieved anything like that, including Einstein, although we'll come to Einstein later on. And so Newton's contribution, and then expanded by other great physicists and mathematicians like Luigi Lagrange, interesting personality. Well, actually, I gave away. I was going to ask you what nationality Lagrange was of. What nationality do you have? I said you probably would find Louis Lagrange, so would say French. No, he was Italian, from Turin, and so Luigi, and he actually worked mainly in Germany, in Berlin, but then finished his career and his life in France, but was Italian. So, and Hamilton's equation. Well, these names will sometimes come back in sort of modern manifestations of these concepts in quantum mechanics. So there are mathematical and physical constructs which are called Lagrangian, like it's a functional, and there is a Hamiltonian operator derived from these names, the people who invented them in the context of old physics, but so powerful that they survived the transformation, the revolution into quantum in a different form. And then, so classical mechanics, then electromagnetism, which is the basis for all of that, including this, because we understand that telecommunications and TV, radio, like modern optics, electronics, all of it involves electrical and magnetic processes. And James Clerk Maxwell is credited with creating this amazing edifice, deriving, I should say, 4 fundamental equations of electromagnetic fields. So, field of electromagnetism, without which we would still be more or less in the cave, chiseling slowly some spaces in which to live, and then some other people on the way, scientists who helped him. He actually put it all together, but Ampere, Faraday, Ohm, and others provided the inputs from different angles. So Maxwell's equations, Newton's laws, Maxwell's equations, and then we have thermodynamics, which, by the way, it's another kind of historical tidbit, and this is technology, right? So the course about technology, future of technology in medicine, this is technology in science, plays an enormous role. And thermodynamics, as a case in point, was created as a result of the demand for more efficient engines, heat engines, locomotives, railway transportation, etc., mechanical engine design, Carnot cycles, eventually automobiles, and so on. So thermodynamics is the field that explains how to understand heat, transformation of heat, transformation of work into heat, etc. And these are the names of the people that played critical roles in the development of this, engineers and physicists. And Gibbs was actually, you're an American, right? He was the first great American physicist. I think it was John Willard Gibbs, if I remember correctly. So really on the firmament of science, that was the birth of American science, and now of course it's US science versus the rest of the world, winning 100-0, more or less. More or less. I'm joking, but that goes toward the mid to late 19th century now. Some thermodynamics and of course industrial revolution. We call it the first industrial revolution, right? When we started building machines and developing modes of transportation. Carnot, French engineer who developed the Carnot cycle. And then that led to deeper understanding of what's going on in systems of many particles. So far, there wasn't anything about molecular nature of interactions, and statistical mechanics was born out of this need to understand how molecules collide with walls of containers and exert pressure, and what happens when you squeeze them, how they react. And what is the concept, what is the definition of temperature? How do you define temperature at the level of molecular interactions? So that was the field called statistical thermodynamics. Now we call it statistical mechanics. Again, mechanics comes back in a different form as a word, but it's kind of misleading because it has not much to do with mechanics. It's really statistical thermodynamics, dynamics of many objects interacting at finite temperature. Okay, so now Boltzmann is his name is spelled in boldface because Boltzmann was, and I'll sort of stop these historical anecdotes. It's a separate topic maybe, but Stefan Boltzmann is worth mentioning. He was an Austrian professor of physics at the University of Vienna, a lone genius actually, who came up with this whole idea of linking microscopic properties of objects such as temperature, pressure, with microscopic interactions. And you may have heard about the Boltzmann distribution. He also came up with the concept of entropy and the laws of thermodynamics, the 3 laws of thermodynamics. We had the 3 laws of mechanics due to Isaac Newton, and we have the 3 laws of thermodynamics due to Boltzmann. Boltzmann was so visionary and so misunderstood at the time. Actually, sadly, he committed suicide because he could not communicate his ideas to the community of peers, not the public, the peers couldn't understand him, and he was so disillusioned by this. Now we understand how powerful this concept of entropy and increasing entropy of systems in isolation, and also related to it is information. Information is also called negative entropy. The opposite to entropy, the creation of disorder, is information, creation of order, or encoding of some information by lowering entropy. Why is this important? Actually, cardinal aspect of living systems. All the living systems have this property of lowering entropy as a result of their being alive. You know, when the life of an individual ends, entropy increases. Until that point, entropy is decreased. We consume, metabolize nutrients in order to maintain structure, in order to improve our performance, knowledge, etc. All of it is a fight against entropy. So life is a struggle to conquer entropy, and that's Boltzmann. And we'll come back to it. I'll just tell you now. One of the greatest physicists of the 20th century, one of the creators of quantum mechanics, Erwin Schrödinger, another Austrian, he wrote a book in 1943, I believe during the Second World War, called What is Life? And in it, he came back to Boltzmann, his fellow countryman, Austrian, and tried to understand why living systems reduce entropy. Okay, so we have now arrived at the point, after 25 minutes or so, we covered, what, 250 years of the history of science. We have arrived at the end of the 19th century. At that point, the world at the end of the 19th century seemed very well organized. Politically, socially, there was hierarchies and empires, the Austrian Empire and the British Empire ruling the world. And physics too seemed so beautifully constructed with these 4 fields, you know, covering most of what people knew and needed, they thought. So at the end of that period, Albert Michelson, sometimes this statement is attributed to Lord Kelvin in his address to the Royal Society in London, but it was Albert Michelson who stated that it seems probable that most of the grand underlying principles have been firmly established. The future truths of physical science are to be looked in the 6th decimal place. In other words, the belief was there's the end of physics, now it's the next era will be the era of engineering, of applications. There's nothing to be discovered. How wrong was he? Very wrong. That was on the precipice. Only 6 years later, there was the greatest scientific revolution taking place with the advent of quantum mechanics. So, and then of course special relativity, and then of course molecular biology, etc., etc. Everything burst on the scene together with all the political and social upheavals of 20th century that we all know and commiserate about, and all the October Revolution in Russia, and then the First World War and the Second World War, and hopefully not Third World War. So these were the scientific revolutions that followed. Special theory of relativity, 1905, Einstein. General theory of relativity, 1917, Einstein. And they completely shook up the foundations of physics. Newtonian mechanics was made not irrelevant or redundant, but incomplete. because it did not explain what happens when objects travel at a very high speed, close to the speed of light. You couldn't use Newtonian mechanics in those cases. The same with general theory of relativity, which basically told us that there is no such thing as, so the first special theory of relativity put a question mark over the concept of absolute time, the concept of time as a universal, absolute, objective quantity. It's not. Time is subjective, it's not universal, it depends on the frame of reference. And this general theory of relativity put a question mark on the concept of space. Space is not objective, is not, Cartesian. Descartes, I forgot to mention his indelible influence on our thinking, even today, 300 years later. So we still think that there's a rigid coordinate system X, Y, and Z, and it's always like that. No, space gets curved near massive objects, such as, of course, black holes and planets, and especially stars and galaxies. So space is not Cartesian, three-dimensional X, Y, Z coordinate system, and time is not what we think is. And anyway, it's interesting anecdotes how people came up with these ideas, and sometimes, like in the case of Einstein, I highly recommend reading his biography, because he already had these concepts in a very nebulous and, of course, naive, primitive form when he was a child. He was thinking about astrophysics and distant objects, and then when he was an unemployed or semi-unemployed PhD graduate from Zurich working in the patent office, he actually got a patent on synchronizing clocks at different railway stations. At that time, there were no time zones in Europe or elsewhere. So the time, of course, was according to the sun, and that changed as you traversed the continent. So that gave him the idea of time being relative. Okay, so these interesting incidents, seemingly random and unexpected for sure, lead sometimes to great revolutions. Without these two things, especially the first one, but also the second, we couldn't have GPS, by the way. Yeah. And it was all Einstein's dream at first. And then, of course, we have quantum mechanics, the third revolution in physics within the space of 20 years. Right? The very foundation that were built meticulously for 250 years crumbled one by one. Objective time, objective space, and then determinism par excellence, which was part and parcel of classical physics, that you could, Newton's equations, you give me the initial conditions of the particles, I'll predict what they will be anytime in the future. Nothing like that exists anymore. So these are the names. Max Planck is credited with the first opening of the gates, floodgates, for quantum physics. You'll see in a minute what he did. And then Erwin Schrödinger, I mentioned, Werner Heisenberg, Wolfgang Pauli, and Paul Adrian Dirac. These are some names. There are many more, and I encourage you to take physics, quantum mechanics especially, but maybe some of you will, maybe some of you won't. And then, of course, I mentioned quantum chemistry. So in the next half a century, physics concepts penetrated into the field of chemistry, and then molecular, so biochemistry, partly, not really completely, but there are some aspects like some enzymatic reactions require quantum calculations. And quantum field theory further deeper in the elementary particles, subatomic, so deeper than protons, neutrons, quarks, Higgs bosons, and so on. And then these are the revolutions. So at this, again, we're at this point, a century and a quarter later, thinking that we are at the cusp of completion of the grand unified theory. Just gravity is not fitting into it. If we could only put gravity with quantum, then we'd have everything. I suspect something else will happen, and then we'll discover something even more exotic than quantum physics. But for now, I think it's as exotic as it can be. So then I listed also other revolutions in science in the 20th century. Of course, the discovery of DNA, that's 1954, if I'm not wrong, 54, something like this, 54, 5 maybe. And of course, the birth of genetics, molecular biology, structural biology, and now a hint of quantum biology. So we've arrived at the reason or rationale for quantum biology as a natural progression of science. Natural. So from the point of view of an imperial physicist, myself, I see the physics idea spreading to other fields. Chemistry is a natural, some people say, subfield of physics. And cell molecular biology is very close, biochemistry, right? So these things already use a lot of physical concepts, thermodynamics, right? Gibbs free energies and so on. But remember, Gibbs, this is end of 19th century, so yeah, there is a need to go deeper. So this is the timeline for this one revolution, quantum revolution. Yes.
Just on the last slide there, you said that quantum was just the natural progression. Where does string fit into it? Is it a separate thing? Or?
In my opinion, nowhere.
No?
I really have very low regard, and maybe turn off the camera, for string theory. This is a very beautiful branch of mathematics, but there's no hope of, at least from today's perspective. Who knows what will happen in 100 years? But there's no hope of ever empirically determining the properties of strings and their role. So as a physicist, I forgot to mention, what does it mean to be a physicist? It means to understand the world, nature, including biological world, using the language of mathematics. So describing quantitatively, but also empirically. That is, your theories, your equations, or predictions, string theory must be experimentally provable. Otherwise, it's not physics. If it's not to be demonstrated experimentally, it's not physics. That's another reason why I don't talk about religion, spirituality, all this, because this is outside of the realm of what I know. It may all be true. Maybe strings exist. I don't know, but as a physicist, I have to reject it as an artificial, mathematical, exotic, beautiful construct, but not physical. Okay, so let's come down to Earth and think if we understand DNA from the point of view of quantum mechanics, we'll be really, really doing something fantastic. So this is the timeline. I mentioned Max Planck, 1900, energy quantization. The word quantum, it comes from this one aspect, actually, of quantum physics, namely energy coming in packets of integer value. So 1, 0, no energy delivered or expanded. 1 quantum, 2 quanta, 3 quanta, but not 2.5 or 3.75. It's not quantum. In classical, you have continuum, right? You have the x-axis, positions or velocities, always a continuum. In quantum, is discrete. All right. Again, I don't want to be too pedantic, but so I'll be using some mental shortcuts. Somebody who is watching me now will argue, yeah, but all right, I know, I know. So then we have 1905, Einstein. So that was the miraculous year for Einstein. He wrote 3 fundamental papers, one of which was on special relativity, one on the photoelectric effect, which earned him the Nobel Prize. He never got the Nobel Prize for either special or general relativity. He got it for the photoelectric effect, which we'll briefly touch on in a few minutes. And then, but there was an experimental experimental demonstration of the fact that electromagnetic waves are quantized, and that's a big deal. because until then it was again, waves, like water waves, like so. It could have wavelengths, any wavelength you want, and any number of any amplitude, but not so here. And then 1913, another monumental discovery. Niels Bohr in Copenhagen explained the structure of the atom using the solar system analogy, the atomic energy levels, and the again experimentally demonstrated atomic emission and absorption spectra, which, by the way, is huge because all of spectroscopy stems from this single insight. And now we can, even today I read on the newswire that some scientists from, I think from the UK, they analyzed light from a distant planet in a galaxy 100,000 years from now, from here, 100 light years away. And they discovered the presence of dimethyl sulfate, which is only produced by living systems,
Wow.
which is a big deal, right? So you look at the light beam coming from a galaxy somewhere, far away, and then you see there's this spectrum, there's this particular line in the spectrum which is related to this organic molecule. So there must be life somewhere else. Maybe primitive, who knows, maybe not, maybe very advanced. Okay, so now we have Louis de Broglie in 1924. I mean, the cast of characters is amazing. We talk about these people probably for lectures, just about who they were and what they were thinking and doing. But suffice it to say that he was a count, Louis de Broglie. He was a count. He didn't bother with undergraduate education, just jumped into a PhD and got a Nobel Prize for it. So, crazy people, but very smart. And then we have 1925, Heisenberg and Schrödinger. So this is now, so from wave mechanics we go into quantum mechanics because it's now put in a mathematical form. You see, I told you physics is uses the language of mathematics. And sadly, again, my social commentary, in this world, in the present day, we are, as a society, illiterate mathematically. People don't understand the simplest things. And we rely on computers and calculators and, punch the number. You cannot do it in your head. So anyway, that's the language of physics, mathematics. And experiment is necessary to validate any pronouncement. And I guess it's the same in biology. You have to have validation. In fact, almost the extreme other end. In biology, there's no theory. It's only experiment. And if you're a theoretical biologist, you're some sort of a crackpot, fringe conspiracy theorist. Anyway, okay, so these are the names and the dates. That's a very historical photo that you may have seen. Solvay conferences. Solvay is a chemical company in Belgium that sponsored these conferences. I don't remember how many, maybe 3, took place in Metropole Hotel in Brussels, which I spent a year in Brussels and I couldn't miss visiting this hotel. It's a bit like a Grand Dame, which is now a little bit, needs a bit dusting and refurbishing. But this hotel hosted these fantastic conferences where you have some of the greatest minds that ever inhabited the planet, including Marie Curie in the first row, next to Max Planck on her left. And then there is, I don't recognize everybody there, but there is Dirac and there is Sommerfeld and there is Einstein, of course, in the same row as Marie Curie, Niels Bohr, and there is Heisenberg in the third row on the right, and so on. So everybody who was anybody in physics showed up, and they collectively, I want to say cobbled together, but it's not the right word. They put together a framework. It's almost like a United Nations climate change conferences, right? They gathered all the people and they talk about what's important, how many degrees will change the climate of the Earth. So anyway, that's kind of on a smaller scale. Perhaps 50 people showed up and they came up with this phenomenal intellectual achievement. So, but okay, let's now talk a little bit about the difference between classical and quantum mechanics in more specific ways. So, as you probably know, in classical physics and engineering, we consider objects to have masses and locations, points in space, and they may be moving, so they have velocities, vectors, components of velocities. They can accelerate. So it's motion and mass. And when they collide, massive objects bounce off each other. Sometimes they stick. So these are inelastic collisions. But they have very well defined identity and extent. Shape sometimes gets deformed, but by and large, identity is there. In classical physics, you also have waves, but these are different things. Waves don't have a mass. Actually, probably, if you think about water waves or acoustic waves or other types of waves, you may be thinking incorrectly that there is something moving. A massive or some particles or dust no, there's no propagation. There is movement, oscillations around equilibrium spaces, but there's no mass movement, transport in other words. So waves are just disturbances of water or any other material in space and time. So we have wavelength, frequency, velocity, and amplitude. I was in Canmore on the weekend, and we went with my wife on a hike around the lake in the Kananaskis area. And it took me about, my wife is a linguist, so it took me about half an hour to explain, illustrate with water waves on the lake, all these properties. So I only have 30 seconds for you guys. Okay, so wavelength, distance between two peaks. Frequency, the time it takes for the next peak to arrive. Frequency is the inverse of period. Amplitude is the size of the disturbance, how much it's moving in and the wave is moving something up and down, let's say, if it's a vertical movement. Okay, so as I mentioned, particles and waves differ classically because particles collide, bounce off each other, sometimes they stick, so, but waves can pass through each other. And if you throw a rock into the pond or lake, you'll see natural waves, and then you have the wave generated by the rock, and they superimpose these other waves, and you can sometimes see them moving separately, right? The waves of the water this way, and your circular waves of the rock create this disturbance separately. So they can, and there are special waves called solitons or solitary waves, which actually pass each other by without any change in shape. These are very special, very interesting nonlinear waves. But typically, you deal with waves which can interact with other waves. We call it interference, right? Interference, and they can either constructively interfere, create a greater amplitude, a greater wave, or destructively they can cancel each other out. If you fly on airplanes overseas or somewhere, you probably have noise cancelling headphones, right? You know that? And these noise cancelling headphones utilize the concept of destructive interference, namely the wave that is coming from the outside would cause you to hear something, some noise, but the microphone itself is generating the wave in the opposite phase, so when the two come to your ear, they cancel each other out, at least partially. So that's interference between waves. All right. So now the question can be asked, physics being experimental, why did these people that I showed you show up in Brussels and came up with a completely new paradigm in physics? Well, because there were these nasty experimental observations nobody could explain easily. And these are the crucial experiments that changed the face of physics around that time. Why am I mentioning this, other than it's a historically interesting tidbit? Because I believe in biology it's the same. We have a handful of experimental observations that are difficult to reconcile with what we know about science in general, biology in particular. And one of these things that the book Quantum Body talks about is, and please, I challenge you to explain to me in classical terms how it is that the human body, composed of 3.7 times 10 to the 13th cells on average. So it's 37 trillion, 37 trillion cells, is organized perfectly, communicates throughout almost instantaneously. If you feel pain, you feel it in the entire body. If you feel pleasure, your entire body is feeling it. How is this? There is no possible way of explaining this like by billiard ball, effects, boom, boom, boom. You sequentially send the signal from here to here, and then, oh yeah, after a million years, it happens. So this is called coherence. In quantum mechanics, the concept is called coherence, that the entire system creates a coherent whole. In other words, they vibrate with the same frequency, all these particles. Anyway, back to the list of experiments which shook the world of physics at that time. So atomic spectra were obtained, and they were sharp, not spread out, smeared out, fuzzy-wuzzy. No, they were very sharp. Hydrogen, helium, and so on. You could tell the two. What's going on. It was really. And that's what led to the construction of the atomic model of the atom by Niels Bohr and others later on. Black body radiation. So that was known for, I don't know, half a century at least. The very precise spectra of electromagnetic waves emitted by objects at different temperatures. We'll come to it. And nobody could explain it. Max Planck, the dean of physics, European physics at the time, and another tidbit, he was the oldest of the photograph was actually quite misleading because it seemed like everybody was retirement age, right? This couldn't be further from the truth. When they made these discoveries, these guys were really young. Einstein was 27 in 1905 when he made these revolutionary changes to the way we see the world. And Max Planck was the oldest of the lot. When in 1900, when he came up with this quantization principle for electromagnetic waves, he was 42. He was the oldest of them all. Okay. So somehow I encourage my student, make a revolution in science, because your young minds are curious, and you are not constrained by the habits of, let's say, I taught quantum mechanics I don't know how many times, so it's my second nature, right? And somebody who sees it for the first time says, yeah, but I don't think this is correct, and that's the way to approach it, right? With a little bit of reverence, but not 100% reverence. So black body radiation, photoelectric effect I mentioned. Later on, specific heats of solids. So back to thermodynamics, but from a higher level, and Peter Debye explained, and this is important because we'll talk about finite temperature effects in quantum effects. Most people who are in the business think that quantum mechanics only applies to tiny little objects like electrons and protons, and only at very low temperatures, because temperatures tend to vibrate everything, make a mess, right? Fluctuations and so on. And therefore, the human body, which is normally at about 36.6 Celsius, what is it in Fahrenheit? You should know, 97? I don't know. Something like that. Should not should not support quantum effects because thermal vibrations destroy it, as they say. But there's a counter-argument, and this is specific case of solids. Crystals, solids, this desk, this chair, they have tiny atomic vibrations that you don't see because they're too small, the amplitude is too tiny on the scale of angstroms or below. And these oscillations are not random. They're actual waves of atomic oscillations, and these are quantized. So even at room temperature, you can see signatures. If you measure it very carefully, you would see signatures or hallmarks of quantization in objects at finite temperature. So many of the people who attack quantum biology as unrealistic forget that quantum effects do exist at finite temperatures or even room temperatures, but they have slightly different characteristics than if you look at elementary particles. And then it's Compton scattering of X-rays of electrons. So you could see that that's a combination of special relativity and quantum, because electromagnetic waves are quantized and they can sometimes manifest themselves as particles, sometimes as waves, sometimes as particles. Particles sometimes manifest themselves as particles, sometimes as waves. So this is one slide that kind of summarizes the essence of quantum theory. Quantum systems, I'm not going to repeat that, but physical systems exist in discrete states, but there could be an infinite number of states, but well defined. And they can be, this is the hardest pill to swallow, they can be in many states at the same time. So imagine yourself being happy and sad at the same time. Okay, this is a quantum system. Or you can be in any emotional state at the same time. You have a spectrum of states. You would call it a psychiatric disorder problem. But that's what quantum mechanics is telling you, that states could be things like, energy states, different energy levels. A particle can be in a superposition of all these energies. We'll come to interpret it a bit better, but for now just take it as a statement of quirkiness of quantum mechanics. So there's something called the measurement problem in quantum mechanics. So to find out about the state of the system, you have to measure it. And measurements use probes, which could be light, photons, or electrons, particles. But you have to disturb the system to find out what its state is. By the way, in psychology you have that too, right? If you need to find out what you're thinking right now, maybe worried about or happy about, I have to ask you a question. You have to probe you. Sometimes a smile will give away, but sometimes not. In quantum mechanics, as opposed to classical, the process of measurement, the act of measurement, is an act of distraction, because you change the state of the system. As the moment you find out what the state the system was in, the system changes its state. So this is something that you knew it was, but it's not anymore. In other words, and two more aspects related to it. Because the systems are in a superposition of states, we can only talk about probabilities of being somewhere in space, in terms of energy, or in time. Probabilities, not certainties. As in contrast, as opposed to classical Newtonian, Simon de Laplace saying, give me the initial conditions of the universe, I'll predict the future. Complete bunk. You cannot say that even about a single electron, let alone the universe. So non-deterministic. And that's why Roger Penrose, in his books, emphasized that quantum mechanics is the path toward understanding consciousness, because classical mechanics is deterministic. In other words, according to classical rules, we'd all be zombies, robots. So discrete amounts of energy are called quanta, and then you have quotes from these various people putting you to rest. You know, if you find it hard to swallow, you're not alone. Even the Nobel Prize winners didn't quite understand it. But I will give you one anecdote. When I was an undergraduate student, and I took quantum mechanics, we had exercises, sessions of when we would solve quantum problems. And I was given this problem. I was sitting there and thinking how to solve it quickly, efficiently. And this professor came to me and said, "Tuszynski, what are you doing?" And I said, "Thinking." And he said, "You're not supposed to be thinking. You're supposed to be doing." So this was the lesson. When you start in quantum mechanics, they tell you not to think too much. Just do it. Okay, so these are the things that are commonly mentioned about quantum mechanics. The classical physics explains macroscopic things like the chairs, but I told you not quite. Quantum mechanics typically, again, is related to microscopic things like atoms and below, maybe some small molecules. But there are also, strictly speaking, macroscopic quantum effects, and in fact very important effects, such as superfluidity, superconductivity. You must have heard about superconductors. This field alone, I think, earned at least a dozen Nobel prizes to various scientists working in superconductivity and superfluidity. Lasers, so this is now common, right? Lasers, QR codes, all of this is quantum. By the way, we don't talk about it, but this is a quantum fact. Laser action is a quantum phenomenon. It's optical coherence. It's a transition between quantum states of the material that produces this laser light that leads to a single wavelength. And phonons, crystal dynamics, I mentioned to you, solid state objects also have quantum properties. All right. Now, what was the saving grace for physics at that period is that, unbeknownst to the mathematicians of the 19th century, they developed the entire toolbox for physics, quantum physics. All of the concepts that required really sophisticated mathematics were already there. And this, in functional analysis in particular, Hermitian operator calculus, and so on, which some of these brilliant physicists were familiar with, and then they employed. Without mathematics, there would be no quantum physics. Without this really advanced mathematics. And you will see in a minute, I will not try to scare you, but I'll show you some glimpses of what this mathematics is all about. But okay, I guess I mentioned all of this before. I just want to emphasize wave-particle duality as a technical term. Duality means that these objects, physical objects, are both particles and waves at the same time. It depends on what the question is being asked of the system. Depends on what the experiment you're performing. You will see either it's wave-like property or particle-like property. And now this is a statement made without any demonstration, any rigorous proof, that quantization of energy and quantum properties gradually disappear as you make the system bigger and bigger. So asymptotically, in the limit of infinite size, everything is classical. So it says. But there's no proof of this. As I told you, superconductors and superfluids can be infinitely large and still quantum. So that statement is kind of sleight of hand. Not quite true. But most of the time, yes, but so what? I mean, there are exceptions. So this is de Broglie, 1923, who proposed this duality, dual nature of matter, waves such as light. And by the way, Sir Isaac Newton proposed already in, 1650 or something like that, that light is actually corpuscular, made of particles. So he was right in a way, but he thought not like we do, right? He didn't think about wave function of light, but he thought that light is tiny little particles, which in some cases, yeah, you can argue. All right, so this is, I told you about light, properties of light like interference and diffraction, right? But you can also observe exactly the same patterns of diffraction when you send electrons or protons or neutrons through a single or double slit. These are classical experiments going back to the 19th century when this was used for light diffraction, finding the spectra. Okay, and this is Max Planck. And that's the formula that changed the world. E, energy, equals N. N is 0, 1, 2, 3, 4, 5, so that's quanta. H times F is the product. H is a constant. We call it the Planck constant. F is the frequency. So this is the first time that anybody in the world related frequency of some vibration to energy. The higher the frequency, the greater the energy. So that's the first amazing thing of this formula. Very simple formula, but probably one of the most powerful formulas in the world. Energy, so frequency and energy are proportional. Remember, E equals mc squared, right? So Einstein said mass is proportional to energy. E, energy, equals m, mass, and c, speed of light squared. This is different. E, energy, equals this times frequency, but quantized. So energy of oscillations or frequencies are in discrete packets. Forget this 1/2. It's the so-called ground state. And actually, it's important to say that the lowest energy state in quantum physics is not static. So we think, let's say, if you think in classical terms, like you have a half pipe. Do you do skateboarding? Anybody here? Maybe not. But you know what skateboarding is, right? So you go on a half pipe and you have some kinetic energy, so go up and down, and eventually you run out of energy. You're stuck at the bottom of the half pipe, right? Well, in quantum physics, the bottom is always moving. You're never at a standstill. The lowest energy state is called 0-point oscillations. And that's this 1/2. Now, this tiny letter H, a Planck constant, is probably the most important physical constant in the universe, and it's precise, and so Planck got it by fitting experimental data to his model, his equations, and got this constant. And this constant is what we call a universal constant, and we know it, we believe it's the same constant everywhere in the universe and never changes over time or space. It's fundamental and universal. We don't know why it is so. The number, let's see, I'm going to rush. Here's the value, 6.6261 times 10 to the minus 34th joule times second. The units are energy times time. This, again, shows up in various manifestations. We'll come back to it later perhaps, but it's a universal constant that Planck obtained by curve fitting. You know, curve fitting in physics is like the lowest form of labor. Like you're dirt, you know, you do curve fitting, right? Instead of thinking and coming up. He did the curve fitting and obtained the most important physical constant in the universe. He did more than that, of course. But anyway, that's the Planck constant. I'll tell you in one of the lectures, maybe the third, something that nobody has seen yet, I think. And so keep it in mind. I call it the physical Planck constant. I'll show you what I call the biological Planck constant. Okay, so there's something like that, in my opinion, that pertains to biology. These are some equations which Planck derived to explain what was known for about 50 years, these spectra. These spectra, so the power intensity of emitted light as a function of temperature. So the higher the temperature, the sharper the peak, and the lower the wavelength, and the wavelength changes to the right as the temperature is reduced. So this was empirical, and everybody tried to explain it, and Planck was the only one who managed. And again, an interesting tidbit of historical perspective, because Planck was, I think he was the chair of physics at Göttingen University. It's a very prestigious school at the time, and very well-known person in the physics community. He came up with this outlandish, outrageous idea that energy cannot be anything. It has to be n times h, 0, 1, 2, 3. And that was accepted. Right? Now imagine if Planck today was at a less well-known position, in a less well-known place. Let's say, assistant professor of physics at the University of Alberta. He would be laughed out of the conference when he would announce it. Right? So there's a little bit of this hierarchical organization of science, maybe a lot of it. And I think it's the nature of things. I'm not making a judgment, is it good or is it bad? It's just the way it is. Right? Physics and science is organized hierarchically. You had American Physical Society, you had the president, vice president, you have the executive board, and you have famous physicists and Nobel Prize winners. So I encourage young people to be outrageous and original, but that's the counterpoint to it is, yes, but you have to reach a certain level before people listen to you. And Einstein, of course, that's another incredible thing, because when he published these amazing papers, he didn't even have an academic position. He was a clerk in the patent office. And by the way, when he graduated, second last from the bottom of his class, so that's encouragement to young students whose grades are pretty low. He couldn't get a research position anywhere in Europe. He wrote application letters to every single department of physics in Europe and well, mostly he didn't get any rejection, no reply, but everything else was rejection. And then he wrote these papers, got the papers accepted, I don't know how, and became a rock star of physics in the space of several years. And they offered him professorships, at Cambridge, for example, and he went to Cambridge. It's too stuffy, I don't want to be here. So he ended up at Princeton. They created this Advanced Study Institute at Princeton basically for him and people like him who were refugees from Europe around the time of the Second World War, and many of them were Jewish because of the Holocaust, and also in the U.S. at the time there was a bit of anti-Semitism, so it wasn't so easy to get faculty positions at Harvard or Yale if you were Jewish, but whatever. Okay, that's another. All of it, I think, is part and parcel of the history of quantum physics. So I'm saying these things to lighten things up, but also to give you a bit of an insight. So the photoelectric effect, very quickly, is when you shine light in a diode on a plate, emitter plate, and if light has sufficient energy or low enough wavelength or high enough frequency, same thing, it'll eject an electron from the surface of the metal, and the electron will then travel to the collector plate, the cathode, and the current will flow. So you can measure it, and the amazing thing was that that's what Einstein explained and got Nobel Prize for it, that there's a very well-defined energy level of the electron on the plate. And you need to deliver sufficient amount of energy, that plus more perhaps, the extra would be kinetic, to release the electron from the plate. And that amount of energy has to be equal or greater, it has to be exceeded by the energy that a quantum of light holds. So high energy light is blue, violet, and low energy is red, yellow. So in this case, you would see that, let's say, red would not be sufficient to cause any current to flow because they would not, the electrons would not be ejected, but blue would. And by the way, in biology, we'll talk about biophotons also, emission of light by living systems. And there is infrared, which is lower energy than visible light, and ultraviolet, which is higher. As you probably know, ultraviolet is dangerous because it can break DNA and cause genetic damage and so on. So that's what he explained. And if you go to any reputable airport and visit their washrooms, you put your hands under the tap, you'll see that water starts flowing. This is the photoelectric effect at work, because the light is, when the light is shining, the current is not flowing. The current is flowing, but it's organized in such a way that the water is not flowing. Then you break this, put the hands under the tap, and the light stops shining on the electrodes, and then you break the circuit, and then that causes water to start flowing. So it's kind of a 0-1 system. Yes.
Is that how automatic doors work by any chance? Or
Yes, the same thing, exactly. Photo detection, photo detectors, photo cells, photoelectric effect. And I will finish in a minute or two. This is a good point to finish. Why is this important? This was the second most important experiment that led to the birth of quantum mechanics. The first was explained by Max Planck, the second by Albert Einstein. This is what we will talk about next time, discussing the birth of quantum biology, because the analogous effect to the photoelectric effect in biology is photosynthesis. The capture of light by chlorophyll of leaves and some bacteria, and transformation of the light energy into the electron energy, and using it to make glucose and so on, utilize it biochemically. So it's a complete analogy, and because this was at the beginning of quantum physics, now when we talk about photosynthesis and explaining quantum mechanically, we'll talk about the birth of quantum biology. So I'll stop at this point, and we'll see you next time.
Okay, great. So I just wanted to tell the students that you're not responsible for formulas or details or calculating stuff, just the big picture, the overarching principles.
Yeah, and actually it's the right approach, because we don't want you to solve any equation, but if you start thinking about these concepts, it's like Einstein when he was a kid, right? Came up with this idea that time is not universal.
Yeah, they'll come up with big ideas, just like that.
Yes, maybe you'll explain something in, what is your field, by the way?
I'm in physiology.
There you go, wonderful. You?
Geology.
Excellent. I don't know about quantum geology, but who knows?
Okay.
Could be you could start a new field.
Yeah, cool. Excellent. Thank you, Jack.
Physiology for sure.
Very, very much.